Okay, in this section, we're going to take a look at systems of inequalities. And we've already talked about inequalities as well as systems of equations. So this just combines those two concepts together. So the solution to a system of linear inequalities is going to be the overlapping bounded regions. So if I have, say, my x and y axis, and I have some sort of equation here, and this perhaps gets shaded below, and I have a second equation off in this direction. This one perhaps is shaded above. Then the solution to this is the overlapping region. So any point that falls in here or on these two lines. Now again, you have to be cautious of your signs, because if it is not equal to, these are dashed lines and do not include the values. So if we take a look at a couple examples, it's relatively easy to verify whether a point satisfies the system. I have x minus y is less than or equal to 3, and 4x plus 2y is greater than 1. So I have the coordinate 2, -1, which contains a value for x and y, and I can simply just substitute these into both of the inequalities to verify that it checks. So if I take the first one, x minus y, that's going to be 2 minus -1 less than or equal to 3. And then the second one, I'm going to plug in 4 times the x value, 2, plus 2 times the y value, greater than 1. And then I just check them. So I know that 2 minus -1 is 3. 3 is less than or equal to 3. That one checks. And I have 4 times 2, which is 8, plus 2 times -1, which is -2. And that is greater than 1. This would be 6. And that one also checks. So this point lies within or satisfies the system of these two inequalities. I can also solve both of these for y, graph it in my calculator, and see if the point falls within the overlapping bounded region. So we'll do the same thing here for b. I'll check the first coordinate. Again, that's an x and a y value. So I plug in -1 for the x, minus the y, less than or equal to 3. -1 take away 2 is -3. That is less than or equal to 3, so that one checks. 4 times -1 plus 2 times 2, greater than 1. That's -4 plus 4, greater than 1. -4 plus 4 is 0. That is not greater than 1, so this one does not work. So this -1, 2 is not within the overlapping region. So this one does not check. And we do the same thing here for C. And -0.5 is less than or equal to 3, so that checks. Four times 0 is 0, plus 2 times a -0.5 is a -1, greater than 1. That one again does not check, so this point is not in the overlapping region either. So very simple to check to see if a single coordinate satisfies the system. You can just substitute the coordinate values, the x and the y, into the inequalities. So let's take a look at graphing them. When I look at the graph of these two inequalities, I have y is less than or equal to -x plus 1, and y is greater than x minus 3. So both of these are just linear inequalities, pretty simple to graph. They're already in slope-intercept form. So my first one here just has an intercept at 1. Mark that point. Has a slope of -1, so down 1, 1 over. Continue that. Solid line, and then they shade below because it is less than. And then on the right side here, I have an intercept, again, of -3. So I plot that point, the slope of 1, 1 up, 1 over, 1 up, 1 over. It is a solid line because, it is a dashed line. A little tough to make out on this. Hopefully your copy looks a little better because it is not equal to, and it is greater than, so it shades above. Then when I look at these two specific inequalities and I combine them as a system, we simply combine the two graphs, and any solution to these falls within this bounded region. And it could be on this line, however this line is dashed. So any point that falls on this would not be included in the solution set. So let's look at some examples and we'll graph them in our calculator. So again, my favorite form, y equals mx plus b, very easy to graph your slope and intercept. So when we look at the first one here, we see this one is x is less than or equal to 2. So the way I remember this is whenever I just have an equation with x, that tells me that it only intersects the x-axis and it never touches y. And the only type of line that does that is a vertical line. So I know that x is less than or equal to 2 is a vertical line that only touches at 2. So it doesn't matter whether my point's up here, this coordinate is 210, or here, which is 2, 0, or down here at 2, negative 10. The x value is always going to be 2. And we see that it is less than or equal to that, so I did draw a solid line. And less than, I see my values as I move off to the left get less, so this one shades to the left of that line. And then I graph the second one. Y is greater than x plus 1. Here's my y-intercept right here, plus 1. So I go to 1 on y. I plot my first coordinate. And this one has a slope of 1 because it's just x, so there's a 1 in front of there, 1x, which tells me I move up 1 over 1, up 1 over 1, up 1 over 1. And this one is also a solid line. So it looks something like that. And then it is greater than or equal to, so it's a solid line again, and it's greater than. So this one shades above the line. So again, anything that falls within this overlapping region is a solution to this system. Now this question here references up above is the intersection of the boundary lines in the solution region. And in that prior set it certainly was. The point of intersection is part of the solution because both of those inequalities, if we go back and look, both these inequalities were greater than or less than or equal to. The equal to component is what's important because if it fell right here at the point of intersection, that is on both of those lines and it is part of the solution because both of those lines are solid. So let's look at this example. So these ones require a little bit of manipulating. So I'll go ahead and write them over here to the right. And I'm going to go ahead and start by subtracting an x from both sides here. Subtract 4x's here. Again, I'm just trying to get them in the slope intercept. And I'll rewrite. So this is 2y greater than negative 4x plus 1. And this one is negative y less than a negative x plus 3. And now in order to change these, I'm going to divide this one by 2. Divide this one by negative 1. One thing to remember about these inequalities, when I multiply or divide by a negative, I'm going to end up flipping the symbol here. You'll see that in just a second. So 2 over 2 is 1, leaves me with the y. Negative 4 over 2 is a negative 2x plus 1/2. And this one, it flips the signs here, so that's going to become just a positive y. It's going to flip my symbol, and then I have negative over negative is positive, so that's x. Positive over negative, minus 3. So here are my two inequalities. I'm going to go ahead and graph these and take a look. So the first one here is x minus 3. So I'm going to go down 1, 2, 3. Plot my intercept, has a slope of 1. So that's 1 up, 1 over. Just make a few marks, make it easy to draw a line. Select my line tool. Now again, this is greater than. There's no equal symbol there. So I'm going to go ahead and make it a dashed line. Something looks a little bit more dashed. Dotted. There's a dotted line. And I'm talking about values that are greater than. So that is anytime I am above that line. And then the second one we'll go ahead and plot has an intercept of positive 1/2. So it's right in there between 0 and 1. And then a slope of negative 2. So it's down 1, 2 over 1. Down 1, 2 over 1. And again, this is greater than, but it is not equal to, so it's again a dashed line. So it looks something like that. And then we'll shade it is greater than, so this also shades above. And the solution here is anything within this overlapping bounded region. Now, same question, is the intersection here part of the solution? And we see we have two lines that are both dotted or dashed because it is not equal to. So if it fell right on this point of intersection, that is not within the solution set. If it fell anywhere right on this line or this line, it is not within the solution set. So the point of intersection is actually not a solution to this system. Now, when I look here at the maximum and minimum values of f of xy equals y minus 2x plus 5 for the solution of inequalities defined by the system of inequalities, what I'm going to do is graph all these. I'm going to look at the vertices of the bounded region. And what you're going to see there is that's going to determine some minimum and maximums when I sub it into the formula here. So we'll take a look at how that appears. And this one's kind of a big graph. Let me resize the page here so I can fit it all in. Okay, that should get most of it. Let's take a look. So first what I'm going to do is x is greater than or equal to 1. So that's going to be a solid line. And that is a vertical line at positive 1. Get rid of the dashed here. So that looks like that. And right now we're talking about values greater than, so that's everything over here. So that one's done. Second one, y is greater than or equal to 2. This is going to help us in the next section when we begin talking about linear programming. Y is greater than or equal to 2. So that is a horizontal line. There's only a y in the inequality, so it only touches the y-axis. And that's at positive 2. So a horizontal line. Again, we're talking about values greater than. So that is all of this above it. And it's going to start looking a little bit busy here as I get the remaining three graphed. But right now we're talking the solutions right here. Over here in the first quadrant. And then I have y is less than or equal to 8. So again, this is another vertical line, or excuse me, a horizontal line at 8. And we're talking values less than, so that's going to be all this below. Let's do these. Let's go this way. Right now I'm just going to give a little bit better definition to our shaded region. Right now we're working in here. That's the overlapping region right now. This one needs to be solved for y, so I'm going to subtract an x from both sides. So negative x plus a 5. So I'm going to go up here. Let me start using blue. Up at 5, and then I have a slope of negative 1. This again is still equal to, so it's going to be a solid line. We are talking about values that are greater than, so that again is still all this within here. So we just cut off a little corner here. That is done, and then I've got, let me switch to green. 2x plus y is less than or equal to 14. Again, I'm going to solve for y. I'm going to subtract 2x from both sides, so that goes here. That's up at 14. It goes a little bit off my graph. I go down 2 over 1, so now I'm at 12 over 1. Down 2 over again, so now I'm at 10 and 2. Down 2 over again. Down 2 over again. Okay, so this one looks something like that. And we're talking about values less than. So again, we are now in here. And that's our last one, so I'll make it a little darker. So we're talking. Okay, so that is our region. Now, what we're going to do is we're going to take that formula up above, f of x, y, and we're going to take the vertices here. And the vertices, if I label these, are going to be 1, 8, I've got 3, 8, 6, 2, it's like 3, 2, and 1, 4. And we're going to take these vertices and we're going to plug them into that formula to determine the minimum and maximum values. And once this leads us into the linear programming, we will use that to help us identify whatever it is that we're doing. If we're producing widgets or something else, how many of this, how many of that to produce to maximize profits is a common one. That type of thing helps lead us to a lot of real-world examples when we're looking at some modeling. Okay, so we're going to take this and we're just going to sub in these coordinates. So I'm going to check the values of these points. So I'm going to check first 1, 8, and I'll do 3, 8, 6, 2, 3, 2, 1, 4. And we'll sub these in. So I have f of 1, 8 equals, and I'll sub in the values, y minus 2 times 1 plus 5, and that equals, okay, so 8 minus 2 times 1, 2 times 1 is 2, 8 minus 2 is 6, plus 5 leaves me with 11. Then I evaluate the next one, f of 3, 8, I'll write these all out here, f of 6, 2, f of 3, 2, f of 1, 4, and I sub these in, so I have 8 minus 3 times 3 plus 5 equals, 3 times 3 is 9, 8 minus 9 is negative 1, plus 5 is 4. 2 minus 6 times, whoops, I'm starting to confuse myself here. Let's go back up here. This should have been a 2 from the formula. And then sub in the 3 from here. I'm not sure where I got the 3 from. 2 times 3 is 6. 8 minus 6 is 2. Plus 5 is 7. And plug in the y, minus 2 times the x, plus 5. 2 times 6 is 12. 2 take away 12 is negative 10. Plus 5 is negative 5. Plug in the y, minus 2 times the x, plus 5. And I have 2 times 3 is 6, 2 minus 6 is negative 4, plus 5 is 1. Then plug in the y, minus 2 times the x, plus 5. Negative 2, 4 minus 2 is 2, plus 5 is 7. So we look for the minimum and maximum. I see the minimum value here is going to be the coordinate 3, 2. And the maximum value is going to be 1, 8. So it depends on what we're doing. If we're looking at manufacturing two different products, maximizing profit, something like that, versus minimizing cost, then this may be what I do. I want to produce one of these and 8 of these to maximize. Or maybe I'm looking to minimize costs, so maybe I produce 3 of these and 2 of these. Just depends on the situation that we're given. But that's more so what we're going to be doing with linear programming in the next section. So have your notes completed, bring them to class, and we'll get a little bit more practice.